Good afternoon, everyone, and good morning to Alex. Alex Bihlo works at Memorial University of Newfoundland, Canada, and today he will give us a very interesting talk about PINs, physics-informed neural networks, about how are they used for differential equations. And I give word to you, please.
Thank you very much.
Also, one more question. Is it fine if can the audience ask you in between, or
yeah,
you want?
Yeah, no, absolutely. The more questions, the better, because otherwise it's just me talking to my screen, eh? So any questions you have, just let me know. I don't think I see the chat. No, I can open the chat somewhere in the... So if you want to type a question in the chat, I should be able to see this as well.
I'll let you know if I see any question. I'll read it.
Perfect, thank you. Yeah, thank you very much for the kind introduction to Vladimir and also for Alexei, to have me here and talk to you. I really appreciate it. And so it's an introduction to physics-informed neural networks. I do recognize physics-informed neural networks have become more popular. Basically, every year they get more and more popular, so maybe some of this will already be familiar to you. But I'll also try to cover some of the training difficulties and maybe possible extensions, how to make physics-informed neural networks more robust. I will begin with a super brief introduction to scientific machine learning, just to bring everybody up to speed what scientific machine learning is, and then focus the bulk of this talk on PINs and deep operator networks, and then show a few examples from our own research. And so obviously, like almost any other field of science, machine learning, after the initial breakthroughs some 10 or so years ago, is when AlexNet beat the ImageNet competition and put deep neural networks on the map again. Also, the sciences, mathematical sciences, caught on, started to use methods of machine learning. And so to distinguish between pure machine learning, which some level can be regarded as a subfield of computer science, if you work with a goal to extract knowledge from scientific data sets or tackle problems which are traditionally being solved using scientific computing, then the branch of machine learning you're engaging with is called scientific machine learning. So what's the competitor approach to scientific machine learning? Well, it's basically scientific computing and numerical analysis. So at least over the past 50 or so years, pretty much all of the progress in the mathematical sciences was done using computers, using standard numerical methods. And now for the last 5 or so years, people started to solve the same problems using machine learning. And so what's then the relation between scientific machine learning and solving differential equations? Well, most of the models, at least of, say, physics, meteorology, astronomy, most of the models are encapsulated using differential equations. So if you, rather than solving differential equations with standard numerical schemes, you want to use machine learning for these approaches, well, then you have to use things like physics-informed neural networks. But that's not the only thing that you can do. I think this is what I want to stress here. So scientific machine learning is more than just solving differential equations. It's an important subfield, solving differential equations, but there is other applications as well: data compression, explainable machine learning, novelty detection, and many, many more. But in this talk, I will just focus on solving differential equations with neural networks. And so traditionally, at least for the last 100 or so years, differential equations were solved with what I call classical numerical methods. This would include types of methods such as finite differences, finite volumes, finite elements, but also, of course, spectral methods, meshless methods. There's many, many methods out there, but all of them are essentially standard numerical schemes in comparison to what I introduced here today. And so with all things machine learning coming to the forefront in the last few years, people also ask the questions, hey, can you use neural networks for solving differential equations? And it's a meaningful question to ask because it was shown, obviously, that neural networks are universal function approximators. That means you can approximate any well-behaved function using a neural network, which means that they technically should also be capable of approximating solutions of differential equations. And this is indeed the case. And this is actually pioneering research on this solving differential equations using neural networks was actually done before the most recent surge in machine learning. So that predates, in fact, AlexNet and the breakthrough of convolutional neural networks. And this is a paper that was published in the late 1990s, which pretty much showed how you can solve differential equations using neural networks and an optimization-based approach. And back then, obviously, the computer hardware was maybe not up to speed yet. So really what allowed sort of this method to have its breakthrough was sort of the advent of more affordable GPU computing and sort of more easy to use computational frameworks. So really, it's basically video gamers striving to have better video graphics actually responsible for being able to get these new methods now for scientific computing. And also don't sort of discard really the importance of these frameworks. Before things like TensorFlow, PyTorch, JAX were around, it was really quite an expert task to code up, in fact, algorithms for training neural networks. So this method by Lagarius was then picked up again around like 5 or so years, and the authors of which adopt this physics-informed neural networks. I'm not saying I'm personally a fan of calling it physics-informed. I would call it differential equation-informed neural networks because of course, not every differential equation is sort of related to physics. But that's the name that everybody's using, so obviously I will use it as well. And this is already, as I indicated, because scientific machine learning tries to solve problems that involve differential equations. Of course, physics-informed neural networks are one of the main areas of scientific machine learning today. So what's then the idea? So if you recall what is a neural network actually do, I mean, there's various ways how you can train a neural network, but in sort of the most classical way, you need some data. Either say like focus on the supervised setting, you have some sort of data set which is labeled, and then you just want to map, in fact, your data samples to the label, and then you just solve an optimization-based approach by training a neural network to basically mimic this mapping from your data samples to your label. And this is basically just training purely data-driven approaches, and this has been widely successful as well in scientific machine learning. So you may have heard about people trying to use non-neural networks for weather forecasting. And this is a purely data-driven approach. So there's all the recorded, basically reanalysis data of the weather. People train this large-scale transformer-based models and show that, in fact, this outperforms pure differential equation-based models. So this is what I call data-driven machine learning. But physics-driven machine learning, physics-informed neural networks being part of this, not only work with data, but they also try to enforce differential equations. And if you think this further, you could also try to enforce something else besides differential equations. So for example, conservation laws come to mind, and I'll talk about this briefly in the end. How is this done in practice? Well, in terms of a numerical method, really what you do is you use a neural network as a surrogate solution that should serve as a global solution interpolant for your differential equation over your domain of definition of the given problem. So really what you're training is a solution interpolant. And this is sort of in some way different to, say, a time-stepping algorithm, where you basically compute one step at a time. In a physics-informed neural networks, you just try, in fact, to get the solution over your entire domain of definition of your problem, approximated by one global interpolant, and this global interpolant is a neural network. And again, you know that this technically should work because neural networks should be able to approximate arbitrary functions. So how does that work? This is still on a very high level, so don't worry, I'll give you some simple example on the next slide. But how does one actually do this? Well, one just defines an interpolant. So your independent variables are the input to your neural network. your output are your dependent variables. And then you train a neural network to solve the differential equation. So you have to enforce the data of this differential equation, and the data being the differential equation itself. If you have an initial value problem, then you need to enforce the initial conditions. If you have a boundary condition, you need to enforce the boundary condition. And if you have a combination initial and boundary value problems, well, then you need to enforce both of them. And you do this basically over points which are defined over the domain of your independent variables. And make this precise and show you some graph in a second. But just to show you, this is just setting up an interpolant. So you can think about this as a generalization to, say, an Hermite interpolant. And then the neural network is a parameterized class of functions. Depending on which architecture you use, you have weights and biases for the most part. And then tuning, in fact, these weights and biases amounts to having to solve a constraint optimization problem, where the goal is to minimize, in fact, the errors which are sort of associated to these three contributions of your loss surface. So in this sense, physics and neural networks are a competing approach. I already hinted at this, because they do bypass numerical discretization, sort of replace, in fact, the numerical discretization by fitting an interpolation function. And I'll make this precise now with the simplest possible example, namely a simple ODE in one variable. So this is a simple decay problem. Obviously, you all have seen this. It has an initial condition. We know that the analytical solution can be obtained as well. But now we just try, in fact, to solve this problem as the simplest possible problem using neural networks. So what do we have to do? Well, we have to replace, in fact, our exact solution by a solution interpolant, the solution interpolant being a neural network, so that we approximate the true solution as well as we can. So our input to the neural network is the single independent variable, so that's the time t. Our output to the neural network is the single dependent variable, that's the function u. And then our goal is, in fact, to simply approximate the true solution with, in fact, this neural network-based solution. Here and in the following theta just refers to the weights of the neural network. So those are the weights and biases, which we try to tune so that this equation will be satisfied. I already indicated this. And so then the question is, like, what architecture do you use? And interestingly, of course, in recent years, everybody's working with this transformer architecture, because obviously this is a very general purpose architecture that performs well across different tasks, images, natural language. But physics-informed neural networks still rely on basically the simplest and probably oldest architecture out there, which is standard multi-layer perceptrons. So essentially feed-forward neural networks with a bunch of fully connected hidden layers. After each hidden layer, there is an activation function. And for pins, one of the criterion, you want to use a differentiable activation function. And I'll make sense of this in a second. But obviously also in this field, people experimented with more fancy architectures, such as convolutional neural networks. People tried out transformers as well. And most recently, maybe I've seen this like a few months, I think, and a new paper came out arguing that there is a new class of function approximator called Kolmogorov-Arnold networks, which can replace multi-layer perceptrons. So people experimented with this as well for pins in the last few weeks. So, okay, so this is all.
Short question regarding the architectures. Is it compatible with, for example, graph neural networks? Can you do pins based on them?
Yeah. People try this as well. I'm not an expert on graph neural networks, but I've seen papers on this. And I can speak a little bit about why you want to do some of these things. It depends, obviously, what problem you're interested to be solving, but it also depends a little bit what your underlying domain is of the problem that you're trying to solve. So yes, so people have used graph neural networks as well. It's just, I think the most standard thing that people would be using would be multi-layer perceptrons still.
Could you a bit explain? I do not understand this single scalar input, for example. Yeah, but you don't know the function. How you get then single scalar output?
Yes, that's right. So that's right. So yes, so for neural networks, you can. So basically, if you have given, say, a supervised learning problem, you have an input and you have an output. So you have no control over the input dimension, the output dimension. So that's given by your problem. And that's the same here, right? So if you know that you have, in fact, this differential equation, you know that your input has to be one-dimensional because there is a single input variable, and your output has to be one-dimensional because there is a single dependent variable. So you know that the input has to be a single scalar and the output has to be a single scalar. But then basically what the neural network allows you to do is pass the input through one or more hidden layers. And these hidden layers, in fact, can be of arbitrary dimension. So you get something that sometimes looks a little bit funky, that you have like a single input that's sort of then mapped in the first, say, hidden layer to, let's say, like 20 hidden units. These 20 hidden units are passed to further 20 hidden units and so on. And in the end, they are sort of mapped to one single output unit again. So what you're saying is you're essentially correct. So you don't know, in fact, what's the proper form of this neural network. So should you have one hidden layer? Should you have two hidden layers? How many units per hidden layer? And this is part of what's called hyperparameter tuning. So you have to do this basically by try and error, or trying to find sort of similar problems where people have done a systematic study. And this helps you guide, in fact, the architecture which might be suitable for your problem. Does that answer your question?
Not sure, but maybe on further I could understand.
Yeah, absolutely.
Okay.
I'll make some of this more precise anyway, just to sort of introduce this here from sort of high level, going into the details now, and hopefully this becomes a little bit more clear. So this is just the setup now, right? So okay, we know, given the problem, we have one independent variable, the output is one dependent variable. We know our neural network has to accept one input and map it to one output. And then so the question is, okay, how many hidden layers do we need? Well, this essentially just tells us how much capacity of our neural network has, right? So if you map the input directly to the output, then you have basically one weight and one bias. That's the maximum you could have. And then you would have just two parameters. And so then it's very, very clear, right? If you just have two parameters, you would not be able to approximate the exponential function, right? So you need more parameters, of course, in your network to be able to approximate this function. But basically coming back to this question that was just asked, how many of these, like how much capacity a neural network has to have, essentially depends on how complicated your problem is. For simple problems, you need usually very small networks. For more complicated problems, you might even need multiple neural networks. So think about, you want to capture the evolution of fluids, and the fluid starts out laminar and then develops turbulence. It would be really challenging to model this entire sort of transition from laminar to turbulent flow using, in fact, one neural network. So then, but how do you train this? This is just, okay, now we basically, so if you've studied standard numerical schemes, I mean, up to this point, you could just say like finite difference methods are defined by saying, hey, okay, we want our discretization to be exact for polynomials of certain degree, right? So say if you make the ansatz, in fact, that you want to approximate polynomials of degree 2, then you can use centered derivatives, and this gives you exact, in fact, solutions for quadratic polynomials. And this is sort of how finite difference methods are derived. And neural networks basically just swap out the polynomial interpolant from finite differences with a neural network. That's up to this point the only difference. But the further difference is how you actually, in fact, get the neural network to train. And for this, in fact, you just use optimization-based approaches. And basically, the goal is to use, in fact, your ansatz. This is a differential equation and your initial condition, and design a loss function which incorporates them both. So in our case, well, we have our differential equation. This is here. We have our initial condition. This is here. We can define now a loss function, which basically just says, okay, we want that this thing is 0. Because if this thing is 0, then of course our differential equation holds. And we want this expression here to be 0. Because if this is equal to 0, then we know in fact that our initial condition is satisfied. And then now we have two objectives. So in the language of optimization, those are two tasks. We want to simultaneously minimize those two tasks. So what do? Well, let's just add them together. And I will speak about why this might be a bad idea also a little bit further, but this is how it's usually done. And then you typically include at least one or more scaling constants, because the magnitude of this loss might of course not be the same as the magnitude of this loss. And so you can offset this with a scaling constant. And I want to be really clear here, right? So if you pay close attention, so this is just approximate, this is just approximate, this is exact. And there is a reason for this, because this of course is not defined, right? Like this is just saying, okay, at my initial time t equals to 0, I want my neural network to be exactly the same as my initial condition. But this here, in fact, where do I evaluate this? So I have to make this more precise now. So, but before we do this, I guess this is why we use numerical differentiation. So numerical differentiation, well, what do you do here? Well, you can't compute this derivative analytically, so you have to compute it numerically. And as I say in finite differences, you just derive finite difference formulas. So you replace, in fact, the differential quotient with a difference quotient. In Fourier methods, in fact, you use, in fact, the Fourier series to compute the derivatives and so on. So how do we do this now? So now, in fact, we have to differentiate a neural network with respect to its input. How can we compute this derivative? And it turns out that for this task, we can use what's called automatic differentiation, which allows us to compute this derivative exactly in finite precision arithmetic, that is. And fortunately, automatic differentiation is the same principle that's being used to compute the gradient of the loss function itself. So the loss function, in fact, is a function of the parameters of your neural networks. And then if you want to minimize this, in fact, and use gradient-based optimization, you need to compute the gradient of the loss function, sorry, this loss function here. And as you compute the gradient, so you need to differentiate this loss function. And for complicated loss functions and/or neural networks, this can't be done by hand, of course. And this is why people use automatic differentiation, which is built right into all modern frameworks of machine learning. So you don't have to worry about this yourself. If you use TensorFlow, PyTorch, JAX, you can just define a function that you want your framework to differentiate for you. And it will then use automatic differentiation, which is essentially just a smart way of using the chain rule. And why can you use the chain rule? Well, because a neural network is just a function, right? A neural network is essentially just a composite function, a bunch of matrix vector multiplications interspersed with applying element-wise nonlinear functions. So this is essentially just first-year calculus. And to compute this derivative not by hand, you can use automatic differentiation, which then does this for you. But so the one thing, and this is why coming back to I said here, we want to use differentiable activation functions. So the loss function, so if you use the mean squared error, you use a proper loss function here, proper neural network. The gradient with respect, in fact, to your neural network parameters is a differentiable function. So the loss function is a differentiable function of your neural network weights and biases, so you can compute the gradient. But to compute this expression here, the derivative of the neural network with respect to its input, the neural network has to be a differentiable function as well, which is why you want to use a differentiable activation function, such as a hyperbolic tangent function or a sigmoid function, so that you can compute these derivatives automatically. And then, in fact, computing the derivatives is being taken care of, which is really the main advantage of this method compared to standard numerical schemes such as finite differences, where you have to essentially first discretize, in fact, your domain. and then in fact define a lattice or a mesh or a stencil. And then if you want to evaluate the derivatives in one point, you need information of neighboring points, right? And this can be quite challenging on more complicated domains, which is what physics-informed neural networks don't require. So physics-informed neural networks allow you to compute derivatives in single points. So that means you don't have to have any sort of topological mesh. That means this method is truly meshless. So you don't need a mesh, you just need a bunch of points. I'll talk about this. But one sort of side effect, positive side effect of this is that you can use them readily on complicated domains like embedded surfaces. So if you want to do like study pattern formations on animals, for example, it's like quite challenging, right? Like to define a mesh on like the body of an animal or so. It's like really, really complicated to triangulate and so on. And this is something that physics-informed neural networks can do quite readily. And so they also then by sort of extension scale up to arbitrary dimensions without sort of more complication, right? Because you don't need to scale up your computational mesh as you need in standard numerical methods. And also for problems on complicated boundaries, physics-informed neural networks can be solved. And I'll show you some examples in a second. And so just to give you like an idea now, like how does this work? And I don't know, obviously not everybody might be familiar with deep learning frameworks, but I use usually TensorFlow. And this just tells you like very roughly, still not sort of answering the question what our precise loss function is. I'll come to this on the next slide, but just like how easy this is to implement, right? So all you have to do is basically like record all the operations that are being done on the neural network. This is because you need to keep track, in fact, of your derivative computation. So as you pass through the neural network, you need to make sure that you record all the operations being carried out, because you need them then if you do the sort of chain rule. You need to basically pass through your network again to compute all these components of your derivatives. So you keep track of the derivative, you keep track of everything that happens on the neural network weights, and you keep track on what happens with your independent variable. Then you evaluate your network. So this was our neural network N, which I called. And then as I said, right, to just compute the derivative, all you have to do is just compute the gradient of this function. And so in this case, TensorFlow takes care of this for you. So this is literally a discretization here, and it's not a numerical discretization, it's an analytical discretization, because it computes you the exact derivative in finite precision arithmetic, which is really nice. And then your loss function is just, okay, now I just want that my differential equation should be 0. So you form a mean squared error loss. And for the initial condition, it's the same. You just pass in the initial time, which was 0 for us, compute what's in fact the computed value through the neural network. And you want to in fact minimize the discrepancy between the predicted initial condition and the exact initial condition, which is given. And these are in fact then your physics-informed loss function, the differential equation loss plus the initial value loss. And then to train the actual neural network, you now need in fact the gradient of this loss with respect to the parameters of your neural network. Those were our thetas, if you recall. And those would be the gradients. And then once you have the gradient of the loss function, you can just do gradient descent and try ideally to arrive at the minimum.
Sorry,
so,
I have a question. I'm not familiar so much with the TensorFlow syntaxes, but here you define that you need to watch input, right,
yes,
for the gradient, and you also, so you add it specifically, but at the end you can access gradients with respect to trainable variables without explicitly adding it to watch.
Yes, because as you invoke, in fact, the model itself, so as you define a model in TensorFlow, the weights, in fact, will automatically be sort of watched. So that trainable variables are automatically being watched as you pass it through the network. So you're right, otherwise you would need here a tape.watch model.trainable variables, but TensorFlow takes care of this for you.
Okay, that was the confusion. Thank you.
Yes, yeah, no, it's a great question. But I think the one thing that I really wanted to point out here is how natural this approach is, right? Because if you train a neural network, right, like this inner part here comes from the physics-informed loss function, right? But if you just say blend out, in fact, these three blocks here, this is like just training. In fact, hey, somebody gives you a t0 and you want to predict the associated value. And then, in fact, you want to minimize, in fact, the difference of this associated value with the true value. And then you just compute, in fact, the gradient of your loss function. So this is standard optimization A. And so what's really neat, in fact, that so you can do the discretization part basically in exactly the same manner and in exactly the same framework. So it's a very natural approach, which is why I really like it. So I think this is about the shortest discretization you can form for more complicated equations, because for PDEs, it will look exactly the same. So it's a very concise way of writing an algorithm for solving differential equations. But finally, just coming back and keeping track of where we are. Well, this we evaluated, right? This one here is just approximate A. And so how do we actually evaluate this in practice here? We need this because otherwise we can't evaluate this here exactly. So where, in fact, do we want to minimize our loss function, namely the differential equation loss? And this is an initial value problem. So we just consider it defined over a temporal domain from 0 to TF, T final. And so now we want to just evaluate and compute the solution over this domain only. So this is, again, one of the differences eventually of this over standard time stepping methods. For time stepping methods like Runge-Kutta, you don't need to define a final time, strictly speaking, right? You could just continue one step at a time just to run for as long as you like, right? Here in this approach, you really have to say, hey, what's the domain? How long do I want to solve my problem for? So you need, in fact, to input, in fact, to the algorithm the final time. And then the idea is, again, we try to define a global solution turbulent over this domain and over this domain only. So our solution turbulent won't be defined for anything that's larger than TF, which, again, you could do in Runge-Kutta methods. Runge-Kutta, you could just increase one step at a time to keep iterating. Here, this is not possible. Here, you would have to retrain the neural network or use an operator learning approach, and I come to this in a second. So unfortunately, of course, we can't minimize our neural network on all points over 0 to T final because there's infinitely many points in this interval. And so what we then do is, well, you guessed it, you just sample randomly points, finitely many points of sort of sub-time steps between your initial time and your final time. And you sample n of those, and then you just say, hey, at those n points, I want that my differential equation loss holds. So now we can make, in fact, the differential equation loss precise. So we don't evaluate this everywhere because we can't numerically. We only evaluate this at finitely many points, which are called the collocation points. And so then, of course, like even in the ideal scenario, say this is goes to 0, and it's absolutely 0 after you minimize, in fact, the neural network. That only guarantees you, of course, that you satisfy your solution exactly at n points, but it doesn't tell you that you satisfy the solution anywhere in between. This is one of the, coming again back to this question that somebody asks, hey, how do I know what the neural network should look like? Well, you want to make sure, in fact, that the neural network does not have too much capacity, because otherwise it could do all sorts of funky stuff in between and give you, in fact, sort of a generalization error that's not great at points which you did not include in your optimization. But otherwise, in fact, this would be it in a nutshell. And so on some level, and I know it's not precisely the same, but on some level, this is quite similar now to Hermite interpolation A. So in Hermite interpolation, you define also collocation points. So you have, say, n points, and at those n points, you're given the values, in fact, of your function that you want to interpolate, and you also have derivative values, and then you define an Hermite interpolant. And here it's roughly similar at our collocation points. We don't enforce that the function holds because we don't know the solution there yet, but we do enforce that some sort of more complicated derivative information holds, which is sort of encapsulated as as your differential equation. So this is then in all its glory our neural network loss function, which we try to minimize and already indicated. So these would be, the TIs would be your collocation points. The more you have, provided you can still minimize this function, the more accurate your solution would become. The longer the minimization will also take. But this is basically what you then pass into the neural network optimizer, TensorFlow, PyTorch, JAX, and it computes you the gradient and it tries to minimize this for you. And ideally, once this is minimized, your neural network will satisfy the initial condition and the differential equation at those points, meaning you get sort of an approximation of your solution turbulent. Just like as a quick side note, so how do you compute the, how do you find these collocation points? People typically do this using just random sampling, some sort of hypercube, Latin hypercube sampling. You could also use a regular mesh, but I also want to foreshadow, if you work with partial differential equation or if you work with stiff problems, so problems that might change rapidly, of course, it would make sense to cluster more of those collocation points where your solution starts to exhibit more complicated features. So for example, if you know Burger's equation, so Burger's equation develops a shock at some point. So ideally you have more points close to where the shock is so that you approximate, in fact, the shape of the shock more accurately. So this is also a research field in itself, so adaptive collocation point placement. So if this interests you, people started to do things like H adaptivity or R adaptivity. Basically everything that has been done for standard numerical methods, people now try to also do for pins. And so then there is interesting research that can happen there. And now just to finish, I'll go ahead.
Can I ask regarding collocation points? Do I understand correctly that the input data, like you just have a set of scalars and you want, for training, you have the set of scalars, yeah, and you know what will be the solution of the differential equation. Also, it's just a scalar, right?
Yes. So, but just, yeah, to be really clear, the
training data in this case, it's one array of inputs and one array of outputs for this particular equation.
Yeah, to clarify, yes, you could do this. So this would be a purely data-driven approach. So you're right. So you could just use the exact solution here. And then, like you said, have like the collocation points and you evaluate the exact solutions. Then this would be a purely data-driven solution. So you take your input scalars, you know your output scalars, you train a neural network, and then you're done with it. But this is not what we're doing here, and this is important. I want to stress this. So here, in fact, we do not use the exact solution. Here, in fact, we only sample our collocation points, and at the collocation points, we want to enforce that we learn the solution of the differential equation, and we enforce this by enforcing that at our sort of collocation points, the differential equation holds. So we don't enforce the solution of the differential equation at the collocation points. We enforce the differential equation itself at the collocation points. Does that make sense?
It does. I don't quite understand what we train on. So in this case, like not in case of data-driven neural network, but in this case, yes, what is the training data? We don't have training data. We put training data. We put it in the loss function, basically.
That's right. Yeah, you're right. So I think that's one of the beauty of this methods. You can generate your own data. So the only like actual data you are given is given by the differential equation's initial condition, right? This is the only function value that you're given. So you want to say that at time 0, as you plug into your neural network, you get, in fact, the value which is given. But in fact, for training, in fact, the neural network to satisfy the differential equation itself, what you do is you sample these collocation points. Just to give you like an example, this is how it looks, right? So see, this would be 20 points. And say we want to solve our ODE between 0 and 1, so 1 being our final time. So what this means is that at this point, we want that, hey, if I evaluate my neural network and differentiate it with respect to time, and add, in fact, the neural network itself to, in fact, this expression, that this thing should be equal to 0. This is what we try to enforce at each of these points. This is our data that we train our network on. So this is in stark contrast to data-driven approaches, because we have no data here. The only data that we need is data that we can generate, because we just sample, in fact, as many of these collocation points as we like. And in each of these points, we evaluate our neural network, differentiate with respect to the input, and in fact, form our differential equation, and want, in fact, that this expression goes to 0 at each of these points. Because if this is the case, hey, this is my initial condition, so I know that this should be the initial value, and I know, in fact, that my differential equation holds here as well, then, in fact, you train, in fact, the solution turbulent for your neural network, a solution turbulent for your solution of your differential equation. Does that make sense?
Yes, it does. That's also why I wanted to ask it before, but then when you started talking about collocation points, I thought that if we have some data, then data might dictate which collocation points we want.
And you're absolutely right. I mean, it is a really great question, because I think this is, again, one of the beauties of this method. So part of my research, what I'm interested in now is like tsunami research. And sometimes you're given you're given data, but you're also given, in fact, differential equations. So say if you think about like a tsunami, for example, maybe you measure the height of the water column somewhere in the ocean. So you have some data points. You're not only having an initial condition, you have some data points, but you also want to know, hey, how is, in fact, now the solution propagating? So the data points alone might not be enough. But then you know, hey, this is the shallow water equations. So you also enforce in extra points, collocation points, a differential equation. So I will talk at length about the sort of downside. So right now, this seems like the ideal approach, like flexible, easy to implement, but there's lots and lots of challenges, unfortunately. But one of the upsides of this approach, so by the end, like once you get the more balanced view, will be, in fact, exactly what you just said, right? So you could fully define a loss function component associated to data points, right? Maybe you're not just given your initial condition, right? Like maybe for whatever reason you have access to some values of the exact solution too, right? In a standard numerical method, you could not use those, right? In a standard numerical method, you can only do time stepping. But in this optimization-based approach, if somebody gives you data as well, yes, you can constrain, in fact, the data as well at the given data points, and the data points then obviously cannot be chosen freely. But the collocation points for a differential equation can be chosen freely. Yeah, I hope this clarifies it. So,
the second term with gamma, how actually you calculate it? It's not clear. You have some U0, for example.
Yes.
And then from this equation, why it's not always 0? I miss this point probably.
Oh, yes. So this is not always 0, because if you define a neural network as a standard function, right? So as you plug in, so I mean, just think about, for example, forget about like a neural network. Just think about this as linear regression. So say this is kt plus d, and k and d being, in fact, the two parameters of linear regression. So in fact, so then, yeah, as you plug in fact, t as 0, so then kt is 0, but then you have still d, right? So unless d is the same as u0, before you train a neural network, this will not be satisfied exactly. So as you define a neural network, just and initialize the weights randomly, just the ansatz that you use, unless you choose the bias correctly of the neural network, this term will not be equal to 0. But this can be made equal to 0, and I'll show this in a second. But at this point, it's just if you define a standard neural network, before you train it, this will not satisfy, in fact, this equation, unfortunately. Does that answer your question?
So my impression was what you're saying now, this I saw this regression is taken for derivative, for example, but here here I thought that you just take this formula and put the in formula.
Yes, you put it in formula, right? But again, think about like a linear regression line, right? So like the slope times t plus intercept. So if you plug for the value 0 in, you're still left with the intercept of the line, right?
Okay.
So unless the intercept is the same as u0, this expression will not be satisfied, and then you have to train a network. And for a more complicated network, this is in fact the case. But you're asking a good question, because obviously this is not great. So this question, I like it a lot, because this is one of the things which obviously any numerical analyst should be very unhappy about. Why is this? Because you know the initial condition, right? Like there should be no need, in fact, to learn the initial condition. Like this is given exactly, right? Like the problem dictates you what the initial condition is. So it's not natural, in my opinion, that you have to learn it, right? Like this should be automatically satisfied. And there is ways of doing this, and I'll show this in a second. But yeah, just to show.
You choose gamma, some parameters,
Right. Yes,
like
yes.
one or what?
That's right. So gamma, yes. So this is again one of the downsides of this method, is that there is parameters here, right? Like which you have to choose, right? Like we already talked about, nobody tells you how many parameters your neural network should have, and nobody tells you, in fact, what this gamma should be. And I will talk about this in the next slide, that this is actually part of the reason why this is a challenging problem to solve. And just like to give you like a short answer here is, like nobody guarantees you that the scale, in fact, of this this expression is the same as the scale of this expression, right? Like the rate of change, in fact, of this problem doesn't have to be the same basically as the magnitude of this problem, right? And so then you have to offset this somehow, right? Because if you want this loss to go to 0, you have to make sure, in fact, that all these components go to 0. So if one of them is really large and the other is really small, then obviously the optimizer has no incentive to care about the really small component, right? They will just ignore this and just focus on the large component. And then you get into the training difficulties of physics-informed neural networks, which I will talk about soon. But yes, at this stage, this is just a parameter, and there has been, like the easiest thing is you just set this to 1. The next easier thing is you just try to figure out what are the scales of these two loss contributions. And then you make sure that, in fact, the scales of them are sort of offset by this gamma. And then if the scales change over time, well, that's not great, because then also gamma should change over time, and people have done this as well. And I'll talk about this.
May I ask a question, please?
Of course, yeah.
Yeah, the question is how we generate, as I understand it, we generate our target data or data on which we will learn, we will train our network using formula. So we know how it looks like. So
Yeah.
we know that its derivative is equal its value. But let's imagine experiment where we put tracker at the end of pendulum, and we want to derive, for example, Newton law. We don't know the how exact formula looks like. We cannot put it in our loss function. So what we are doing now, we are basically trying to solve this equation without like solving it. But in some cases, we do not want like numerical solution. We want the solution that dictates how parameters are related, and this is like another approach, right?
Yes, absolutely. It's called the inverse approach. So here we're using the forward problem. So the forward problem is, hey, we know our differential equation. So we know this, right? And now, in fact, we just solve it. So this is then the forward problem, and then we compete against basically finite differences, finite elements, finite volumes, and so on for PDEs. Here, say, Runge-Kudde methods. But what you're asking is called the inverse approach, right? Like you have to solve the inverse problem. Somebody gives you a bunch of data. Like you said, you have the pendulum, you just track, in fact, hey, this is my time. This is, in fact, my position and momentum of the pendulum. And now, in fact, you collect a bunch of data samples. And then the question is, hey, can you recover what the laws of nature are from these data samples? And the answer is yes. And the answer is you can also use physics-informed neural networks for this approach. And there is, well, not only, there is other approaches as well, but basically what you ask would be, hey, you define like a candidate class of problems. Say you want to recover Newton's second law, but maybe you're not entirely sure how it looks like, right? So then you say, okay, based on my sort of intuition, I believe, in fact, that the solution should depend on the solution itself, the first derivative and the second derivative. And then you define basically a class of functions which involve the value of the function, the derivative, and the second derivative. And then, in fact, you use this approach to find, okay, what's the precise form of this function? And for this, you use then the measurement data. So this is called the inverse approach, and people do this as well. And in my opinion, this is actually probably the more suitable approach for physics-informed neural networks, because you don't have to compete against very well-defined numerical methods. So again, this is nice, and I'm not saying that what I tell you here, in fact, is not useful. It's absolutely useful for specific types of problems. But again, the challenge is, right, like here you compete against very good numerical schemes, right? Like Runge-Kudde methods, linear multi-step methods, they have been around for a long time. And you compete against these methods, and it turns out that unless you have specific problems, you will never be, at least as of 2024 August, you just never beat, in fact, the accuracy or the error that you can achieve with a standard numerical method with these physics-informed neural networks. And I can actually show this to you just as we move on. I mean, this looks kind of nice, right? So this is basically just to show you how, as you train a neural network, you get the neural network solution, exact solution for our initial condition. Yeah, that looks great. This is your error. It's not too bad, 10 to the negative 4. And this is your loss function, right? This is the physics-informed loss, right? So it goes down and saturates somewhere like at the loss value of 10 to the negative 7. And this seems on one level quite good, right? But on another level, and I think this is really the main downside of this approach, is you have no guarantee, in fact, that you will ever achieve the global minimum of your loss function, right? So here, what is the problem? So here the problem is that unless, in fact, this loss is equal to 0, of course, this is not exactly satisfied, and this is not exactly satisfied, right? And so that's part of the challenge that you're facing here is, yes, so of course you get some solution and you get some sort of meaningful error, but now somebody who is a numerical analyst asks you, hey, if I in fact increase my number of collocation points to infinity, if I increase my capacity of my neural network to infinity, would my error go to machine precision? And the answer is no. Unfortunately, no, because you're always left with an optimization error. And it turns out like people experiment with this and it gets better every day too. But it is really, really challenging to get, in fact, the error of this method below, in fact, I don't know, depends, of course, on the problem that you're saying, but say like get errors, like mean squared errors of less than 10 to the negative 4, 10 to the negative 5, 10 to the negative 6 becomes really, really challenging, especially for PDEs, which means that unfortunately, this is not a very accurate method. And I think this is part of, and I think we'll talk about this. Let me just, I think because, let me just do this full screen again, because I think I changed the ratio. I think this is part of like what makes neural networks, like physics-informed neural networks, inferior to standard numerical schemes. because you have no basically error estimate guarantee, right? Like essentially in the end, right? So coming back to our code, you pass in fact the gradients of your loss function in a sort of optimization algorithm. And well, I guess most of you work with optimization at some point, right? Like depends how good your algorithm is. It depends how complicated your loss surface is, right? This is in general not the convex loss surface, right? So this will have many local minima. So you might get stuck in a local minima. You might have a very flat loss surface, which means in fact, as you come closer and closer to the minimum, you start to stall. And eventually you just settle somewhere. And there's ways around this and improving this. You can use better optimizers. You can use learnable optimizers. So you can use smaller intervals. So there is ways to improve this further. But I just want to point out here, right? Yes, the method is really elegant. It is really successful. It's been readily adopted. It's like exponential increase of interest over the last few years for sure. But for solving the forward problem, like solving a differential equation itself, you're usually just better off using like finite elements, finite differences, finite volumes for PDEs, or say Runge-Kutta for ODEs. Unless, and this is the question that Ilya was asking, right? If you want to solve the inverse problem, somebody gives you some data, well, then this is really challenging to do with standard numerical methods. And then you have to use an optimization-based approach, in which case, in fact, pins are excellent. But yeah, just to, I spent a lot of time on the ODE case. So I just wanted to briefly show you the PDE case, because the examples that I show you will be for PDEs. And I think the good news, and again, coming back to why I personally like working with pins, like once you understand how they work for like ODEs and how once you've implemented them yourself for ODEs, it's really actually quite easy to implement this for PDEs. And this basically just seems like a copy of the slide that I had for ODEs, right? So all you do is, hey, you set up a neural network architecture, which now has multiple inputs, right? You have a PDE, you have multiple independent variables. If you have a system of differential equations, and you also have multiple outputs. But otherwise, it's the same multi-layer perceptron from before. You just change the number of inputs and outputs, and you're golden. You still enforce that data doesn't change. You have a system of equations. You have some initial conditions, some boundary conditions. And now, in fact, you have just to sample your collocation points on, basically, instead of a line, on like a more complicated domain, like a plane or like a cube or whatever, depends how many independent variables you have. But otherwise, in fact, the physics-informed loss function doesn't change. Everything else is exactly the same as for the ODE case, which is really quite cool, because it means you can readily adopt this for PDEs. And if you have implemented a one-dimensional PDE, say you want to solve the 1D Navier-Stokes equations, you are convinced that your physics-informed network works, but you're interested in the three-dimensional Navier-Stokes equations, all you have to do literally is just sample your collocation points on your three-dimensional domain, and in fact evaluate your neural network for these four inputs instead of the 2 inputs that you had before. So that the adaptation from a 1 to a 2 or 3-dimensional code literally takes you half an hour. And I'm not kidding you. So it's this quickly, which is obviously very different. If you ever discretized PDEs yourself, like in 1D and then change to 2D and 3D, this usually takes you days, right? Like to define the mesh, to define the derivatives and so on. Vastly more complicated compared to pins, again, which is just the elegance of this method. So yeah, this is just I just don't want to spend a ton of time. You have a system of equations, an initial value operator, a boundary value operator, and all you do is now define a loss function that is defined on your system of equations, your initial value operator, your boundary value operator, and you evaluate it basically at the collocation points. And there's collocation points for your PDE, there is collocation points for your initial condition, and there is collocation points for your boundary condition. And then it's already the question that somebody asked before, hey, but now you have a further parameter gamma. And yeah, so this is why, in fact, this problem becomes more challenging. And but yes, so just to give you an idea how these collocation points could look like. So this is when we solve the shallow water equation, the sphere. using periodic boundary conditions. So your initial collocation points, they are just sampled at time 0, and then this would be latitude and longitude. And so then you sample, in fact, these blue points would be your initial value collocation points, which are fed into your initial value operator. The boundary conditions we enforced in a different way, so we have no boundary conditions for this problem. And then our PDE collocation points were sampled on the sphere. It's like the sphere, but also using time. So we integrated for 12 days. So these would be the PDE collocation points where we try to enforce our PDE to hold. This is sort of in a nutshell, like, again, this is why I can rush through the PDE case, because it's exactly the same as we discussed, just that you have more dimensions of your collocation points, everything else staying the same. And I already talked about this a few times, so now I want to review, because one of the things that, I mean, again, like I work with pins, I really like to work with them, and I read a lot of papers on pins. One thing that always bugs me is that I feel that in a lot of these papers, people are not being like totally straightforward with talking about the shortcomings of pins. And so I want to spend a little bit of time, like what are some of the downsides? Talked already about some of these upsides. They're meshless. You don't need to use numerical differentiation. You can sort of quickly adapt like ODEs to systems of ODEs, PDEs to higher dimensional PDEs, and you can use automatic differentiation frameworks like a TensorFlow and PyTorch. So really, really lots of upsides. But so one of the downsides, and you already see it here, eh? So what if now I want to solve my problem instead of for like 12 days? I want to do climate prediction. I want to solve this not for 12 days, but for 12 years. Well, so you would have a really long domain, right? And so the longer the domain you have, the more collocation points you need. And the more collocation points you have, the more costly it becomes to evaluate this loss function, right? So there is like a linear increase in computational cost, the more collocation points you have, obviously. But not only this, also the neural network has to enforce the solution in many more points, right? Which obviously is a harder problem, right? If I give you 2 points and ask you, hey, fit me a polynomial to 2 points, well, you just use a line, right? If I give you 3 points, well, you just fit, in fact, a quadratic polynomial. If I give you like 1,000 points, right? It's a much harder problem, right, than to sort of solve the associated interpolating system to get you interpolant, in fact, in these 1,000 points. And here it's exactly the same thing, right? So it gets a harder and harder problem. The more points you use, and you usually have to use more points, the larger your domain becomes. And also, I think the one thing that I really want to drive home is just going back to the beginning, eh? So in the beginning, I showed we have our initial value problem, right? Like we have 2 conditions. We have an initial condition and we have a differential equation. And then technically we have 2 losses, right? Like we have one loss, which is this one here, and then we have a second loss, which is this one here. And then I kind of basically swept under the rug, oh, let's just add it together. And of course, if this loss goes to 0 and this loss goes to 0, then of course the composite loss goes to 0 as well. But the problem is, right, so that if you add these 2 loss contributions together, the loss surface can be very, very different from the loss surface that you have individually here and the loss surface you have individually here. And in the language of optimization, so this is called a multitask optimization problem, a multitask learning problem, and these are notoriously challenging to solve. And it is well known in multitask learning that simply adding the loss functions associated to each task might not actually lead that each task is learned properly. So if you studied optimization, this is sometimes called Pareto learning. Like Pareto optimization is you have multiple tasks and you try to find the Pareto optimal front, which essentially tells you if you try to improve one of these tasks further, it would come at the expense of these other tasks, right? So there is some sort of optimality over all tasks. And it's not guaranteed, in fact, that you find, in fact, this optimality by just minimizing this composite loss function. And so then obviously just to give you like a brief review also because somebody asked about like, hey, how can we find this gamma? What can go wrong? Well, if you have individual loss contributions, right? So then what you really care about is the loss gradients, right? Because it's a gradient-based optimization that you use, right? So then if the gradient of your one loss contribution, the gradient of your other loss contribution point in fact in opposite directions, then in which direction would you go, right? It's challenging. Same this question, what if like one gradient is much larger than the other one, right? Well, then the second sort of loss contribution would simply be ignored, right? If the gradient is too small, then in fact only one of these tasks would be learned. And like high curvature sort of makes it challenging for the optimization, in fact, to find basically a proper minimum. So there is different ways, in fact, how this can go wrong. And this is one of the things why this is open research, right? Multitask learning is a challenging part of machine learning. And unfortunately, if you work with pins, you have to solve, in fact, multitask optimization problems. And already indicated, so people try then to find better ways of balancing these loss contributions. So say coming here, so say, for example, your initial value loss is very small, but your boundary value loss is large, then the optimizer should maybe focus on the boundary value loss, right? And then you maybe make sure that this contribution is temporarily ignored until, in fact, the boundary loss is small. And once the boundary loss is small, you want to make sure that optimization continues with all of them. So then people try to adapt, in fact, these coefficients throughout, in fact, the domain of optimization by using some sort of heuristics. And it works for certain problems, but in my experience, unfortunately, it doesn't work very well. So I experimented extensively in my own research with trying to balance out these loss contributions. And in my opinion, the only thing that really works well is if you can get rid of as many of these loss contributions as possible. But just to give you an idea, so, and there is a lot of this in the literature and further methods being proposed all the time, people try to come up with ways, in fact, to solve multitask optimization problems for pins. But again, like my favorite approach is, and I think it's the most natural approach, if you can, simplify your physics-informed loss function. And I think it goes back to one of the questions one of you had. It always bugged me, right? Like, why should I have to learn my initial and boundary conditions, right? Like, I know those, right? Like, I should not have to learn them. And indeed, actually, the first paper by Lagares that was proposed on what's now called physics-informed networks, they actually included the initial and boundary conditions at what's called a hard constraint directly in the neural network. And it's, for some problems, very simple to do, right? So for our ODE example from before, rather than just say that our solution is a neural network interpolant, let's just say, hey, our candidate solution should be structured as my initial condition plus t times divided t final times my neural network, which is being learned. And this is now nice because as you plug in t equals t0, no matter what the weights of the neural networks are, this goes to 0 anyway, right? And you're left with it even before you train your neural network, the initial condition is satisfied. So that means, in fact, going back at least for our ODE example, in our ODE example, we don't need to have this loss contribution anymore. And we just have this loss contribution, right? Which simplifies the problem, of course. And so hard constraints, in my opinion, or in my experience, if you can work with them, they always simplify, in fact, the problem. It's usually challenging to find like what's a good hard constraint, because say again, if this is trained now for long intervals of time, then somehow the neural network has to learn to offset the factor of t here, eh? So unless your solution is linear in time, it has to basically learn the solution divided by time, right? And this brings some challenges as well, right? If you have large domains and so on. So yes, you can always find hard constraints. Finding good hard constraints is not always that easy. And I also want to point out, so yes, you can also do this for PDEs. So for PDEs, you can then get rid of the initial and the boundary loss. But if you have a system of differential equations, unfortunately, you always have to deal with a multitask optimization problem. Because if you have a system of two equations, you cannot in fact get rid of these two loss contributions then anymore. So this allows you to mitigate some of the challenges, but it doesn't allow you, unfortunately, to bypass it completely. And also if you have like really complicated domains, right? So again, like you want to solve things like in my case, say for tsunami research, I want to study how a wave hits a coastline. To enforce, in fact, the condition at the coastline as a hard constraint can be quite challenging if the coastline is sort of quite complicated. That's right. There was a question there.
Question in the chat?
Yes. So, yes, that's right. So I will answer this question as I give you some example. Yes, there is advantages. I will answer this question. If you bear with me, I will answer this hopefully in the next few minutes. Because yes.
Can I ask one more thing about how to deal when we have these several components? Does it make sense in case of PDE, for example? Does it make sense instead of addition to make multiplication? Like, yes, you can. You have obvious downside if one of the conditions is easily going to zero, then everything is zero. But maybe in some cases it will help, because then you at least have one less or several less gamma if you just have multiplication of losses.
Absolutely, yeah. So people experimented extensively with different losses. I mean, like my research is mostly like on fluid mechanics, and I've tried to implement so many papers and different ways of scaling the loss functions and so on, and multiplying loss function components together. I have found in my own experience that if you can solve this problem as it is, then you can solve it no matter how in fact you formulate it. And if you can't solve it in this way, then any other combination of like what you can try out also doesn't work out. That makes sense. This is a very, like, of course, limited view, and I know people write papers all the time about different ways of solving this, and maybe are multiplying the loss functions in different ways. In my view, unfortunately, it has never worked. Unfortunately, and the only thing that consistently works for me are these hard constraints. This always works for me. Well, okay, I shouldn't say always. This doesn't work if the solution is a shock. Like this is if you solve like an equation, like a shallow water equation, you want to solve like how the breaking of a dam, right? Like you remove and there is like a shock initially, then you would have to encode in fact your initial condition is discontinuous, and then like these hard constraints also don't work so well in my experience. But for the most part, like this is what I usually try to work with, if I can. But yes, absolutely. So there is a lot of literature out there, and like if you're interested in different aspects of like research, it definitely makes sense to look into, hey, how can I formulate this multitask optimization problem and maybe make it more efficient.
One more question, if I can.
Course, yeah.
Does it make sense to maybe use, if you have data, for example, you're mentioning shock when it's not just shallow water, but you have more abrupt waves. Does it make sense to maybe use symbolic regression, and then if you have data, you predict some sort of equation, and then you put it as a hard constraint?
Yeah, and I know what you're talking about. We tried this out, so we had tried this out, not symbolic regression, but we tried out, in fact, exactly this. So you have a shock, and then we'll try to learn the initial condition, which has a shock using a neural network, and then this approximates the shock, of course, but it's still continuous and differentiable. And then we used it as a hard constraint, but it still hadn't worked as well as just using this sort of soft constraint. So yes, I know what you're asking about, and it's definitely worth trying out. In the example that we considered, and mind you, this was just one example, right? Like just trying to capture shock in the shallow water equations. Learning this shock and then using the learned solution as a hard constraint did not work as well for us as just using the soft constraint. But I think that the neat thing about this is, and I think a lot of these questions that you're having, right? So people started to look into some of this, but there is also like still like lots and lots of research to be done here, right? Which is probably one of the reasons why there's lots of publications in this area. But if you like work in a specific field, like check out what's done there, it's not impossible, in fact, to contribute to the research. In fact, at this moment, still, I would say is a fairly low barrier of entry, which is really good, right? Because we still need better understanding of these methods.
One remark or question. So what? How you explain it? My understanding that it's similar. This approach is similar to checking for something like uniqueness theorem. That let's say boundary defined what is inside the volume. And you check it just simultaneously, what happens in the volume and what happens in the boundary, and they should satisfy both.
Yes, that's right. Yeah, that's it. Yeah, that's it. And I think this is, like I said, this is why it can be challenging, right? Because I think like if you ask me, right, so I think one of the things that's still underutilized in this area is to try to look into better optimizers. So people use these first order methods that are readily available in standard neural networks. And so, but obviously if you work with optimization, like what is one of the methods you would look at? Well, you look into Newton's method, of course, right? Like if you use optimization approaches in scientific computing, people try to use things like Newton iteration and so on. And the reason why this isn't done widespreadly in standard deep learning is, of course, it's like very costly to form, in fact, a full Jacobian matrix, right? If you have a neural network which has, say, 1 billion parameters as ChatGPT or so, right? You don't want to form a matrix that's 1 billion by 1 billion, right? But so interestingly for pins, of course, like you still usually, right, like for simple problems, I'd have to check, right? But I think this pin here has like just a few hundred parameters. So if you use like neural networks which are not overly large, like you have a few hundred to a few thousand parameters, of course you could use better optimizers. You could use Newton's method, or like, I don't know, some of these limit LBFGS, right? So this quasi-Newton methods. And I feel there is still a lot of potential in this area if people start to focus on like better optimizers to get better solutions, right? And then maybe some of these things that as you sort of get stuck somewhere, right, that you can't satisfy what you said, right? You want to simultaneously know what's at the boundary and what's in the interior. And then maybe you somewhat get stuck, right, in a local minimum, and you would be able to sort of get out of this local minimum if you were to use better optimizers. So I think this is still worth the research. And obviously people do research on this as well, but I feel like there is more research done in right now, people just trying to find yet another way of finding what should be gamma I and gamma B, or like what's like a slight variation of the architecture, rather than trying to come up with better optimizers, a better way of hard constraining these conditions that you care about. So I feel like this, at least like this is what my own research is about these days. And hopefully we'll make some progress on this still. But yeah, so I think that the one thing I indicated about, right, that is challenging here is that if you have like larger domains, right, so you need more collocation points, but also, I mean, one of the things which is not great, like if you just change the initial condition, right, not the PDE itself, right, just the initial condition, well, you still have to retrain, right, because your solution, right, like has sort of minimized the weights and biases, has minimized the loss function to give you particular weights and biases for one solution, right? So if you change, in fact, the initial value or the boundary value operator, keeping the PDE the same, you have to retrain the entire network, which is not great, right? So somehow, obviously, this is quite expensive, especially if you have a high-dimensional problem, right? So then retraining is not great, and also long integration times are not great because you need lots of collocation points. And I already indicate that like if you have a long integration interval, pins tend to just fail, right? So typically they just converge to some trivial solution. So think about the harmonic oscillator, right? So it goes up and down like a sine wave, and you want to just solve the harmonic oscillator for, I don't know, like 100 seconds or so. What would typically happen is it behaves like a damped harmonic oscillator. So you begin, in fact, a few oscillations and the solution goes to 0. So that tends to be the case for pins. So they can't optimize if you have a long integration time, unfortunately. So that's obviously not great. Like those are two pretty bad sort of downsides. Can we overcome them? And yes, we can. And this is sort of what still like fairly niche within physics-informed machine learning. But the idea is rather than solving a particular differential equation, you just try to learn the solution operator. So let me repeat this again. So instead of learning one solution of the differential equation, let's just learn the solution operator associated to the differential equation. And once you know the solution operator, you can evaluate it for any initial condition, right? So this basically is then solves both of these problems. But if you know the solution operator, you have learned it, you change the initial condition, well, you just evaluate, in fact, your initial condition using your learned solution operator, and you get, in fact, the solution at a later point in time. But it also allows you to solve the second problem. So if you know you have to solve for long time intervals, just solve it for a short time interval for many initial conditions, learn the initial value operator, learn, in fact, the solution operator, and then, in fact, apply the solution operator in an iterative time-stepping manner. Take one time step, then you get a new final solution. This new final solution can be fed in as an initial condition to the solution operator, and then you can time step. And then you solve, in fact, both of these problems. So this is, like I said, it's not so well known still. This is called physics-informed deep operator networks, or deep ONets for short. And now you should ask the question, hey, like, why does this work? Like, why does it work? Are you guaranteed that this works? So let me take one step back, right? Like we know sort of that pins should work because we know that we can approximate particular solutions with neural networks, right? That's the universal approximation theorem, that any sort of any basically sort of smooth function, say, can be approximated using a neural network. And so then the question is, hey, what about the solution operator though? And this was introduced just a few years ago, but it rests on also a result that's not too old. Chen and Chen had shown that the solution operator, like a linear operator and a nonlinear operator between two Banach spaces, can be learned with a neural network. And so you can actually learn the solution operator using a neural network. So instead of solving a particular solution with pins, now we learn the solution operator. So let me try to formulate this. And this is a little bit hand-wavy because, of course, it depends on what classes of problems you want to solve. But let's assume we have a pure initial value problem. And our goal is, in fact, to learn the solution operator so that if you plug in basically a particular initial condition, and you then care about the solution at some point in time and some location in space, then you simply evaluate your solution operator for this initial condition at this particular spatial temporal point, and you should get, in fact, the associated solution at this point. So the solution operator, you already see, has to have two inputs, so it has to have, in fact, the initial condition as an input, and it has to have the independent variables as an input to get, in fact, the solution for the given initial condition at, in fact, the solution that at the point you care about. And so then if you want to have a different initial condition, you just swap it out, right? And just evaluate the operator, but you don't have to relearn it then anymore. So two inputs required, one for the initial condition, one for, in fact, the independent variables. And so then there is a complication that arises here. So you should already sort of scream, so, okay, but the initial condition is a function, right? So how do I feed a function in here, right? Because a function is an infinite dimensional vector. So somehow this function has to be sampled to be able to be passed into the neural network. And so typically this is done by sampling this initial condition at the finite dimensional subspace. And the easiest way to do this is to define it similar like collocation points. Here it's called sensor points. You just define, in fact, a fixed number of points throughout your spatial domain. And at those fixed points, and those points have to remain fixed each and every time you evaluate your solution operator, you simply sample your initial condition there. And so then this is a finite dimensional input, right? And then you can pass this finite dimensional input into the neural network, right? So these points, T and X, are still sampled at these collocation points. Those are finitely many points as well. And then your function is first sampled at these sort of sensor points. So this becomes a finite dimensional input as well then. And then both of them can be passed into the neural network. And so this is basically how a deep operator network is structured. It requires two branches, two separate networks. The one is called the branch net, which processes the sampled initial condition, and the trunk net processes the independent variable. So on some level, you could regard a physics-informed network as simply a deep O-net where you keep the branch net fixed, right? So you don't change the branch net ever, right? So that means you have to retrain for each new initial condition, and you just focus on the trunk net. And there is many ways how people structure this, but the simplest way, and this is basically comes from this theorem by Chen and Chen, is that you just pass the inputs from the branch and trunk net through two separate networks, and then in the end multiply these networks together via a dot product. So you have your input to your branch net, that's your separate input, sorry, this is your trunk net, that's your independent variables go through one neural network, your sampled initial conditions go through your branch net, and in the end both of these networks output a p-dimensional vector, where p is a hyperparameter, and then you multiply this together, and this gives you, in fact, then the output of your solution operator. And so the nice thing about this is that the loss function is still the same now. So because in a way, it's just generalizing a pin to learning the solution operator. So all you now have to do is you have to train, in fact, not only on your collocation points, but you have to sample your class of functions, in fact, that you care about, right? So say you want to solve the harmonic oscillator. So then you need to know, like, okay, for what range of values of my oscillator do I care about? Maybe I care about P and Q, the position and the momentum being between range -1 and 1. Well, then you just sample your initial conditions between the range -1 and 1. And then like you have arbitrary many of these samples. Say you sample 1,000 different initial conditions, 1,000 different collocation points. And then ideally you learn to train a solution operator that recognizes basically how, in fact, to sort of compute the solution for all initial conditions within your range of values that you sampled, and for all your for your entire domain of your independent variables. Yeah, hard constraining works as well, so you can sort of simplify the loss function for deep O-nets too. And then so the trained deep O-net in the sense acts as a global solution turbulent for the solution operator rather than the solution itself. And I will show you some examples and then I come back to the question in the chat, but just to show you that this works. And what I cared about most, like I said, is numerical weather forecasting and tasks related to ocean modeling. And so what we did like a few years ago, ask this question, hey, does this work for numerical weather forecasting? And if you want to do this, you typically consider what's called the shallow water equations on the sphere. So this would be the simplest model that folks in meteorology would start with today, because it has both fast-moving waves, gravity waves, but also slow-moving waves, Rossby waves. And a numerical solver needs to capture them both. And you want to do this on the sphere because obviously you do weather forecasting on the sphere. And this is, again, typically a challenging problem, right? Because if you use latitude, longitude coordinates on the sphere, you know you have a singularity at the poles. So people in meteorology worry a lot about how they define coordinate systems to avoid the singularity at the poles. And this fortunately was never an issue for us because all we need is collocation points. And as long as you don't sample collocation points directly at the poles, in fact, you have no singularities, in fact, in your system of equations. And then just to show you how this looks like, just to show a few of the standard benchmarks. So this is like one of the benchmarks that people usually care about. So you begin with, basically, this is the water height, and this is the component of U, the component of V solution. And so what you begin with is like basically a zonal flow. So it's basically a flow west to east around the Earth. And you have some sort of initial sort of distribution of your water height. And there is a little mountain sitting here. And I don't show the mountain, but there is a mountain here. And what should happen is that basically as sort of the flow hits the mountain, it starts to create the waves. So we can take a look at this. So you see that there is the mountain here, and then sort of there is a wave forming in the lee of the mountain, and you have these gravity waves that radiate outwards. And so this would be like in the Rocky Mountains, you see something like this. So you have the Rocky Mountains somewhere here, and then typically in the lee of the Rocky Mountains, in fact, so you get this sort of standing wave, and then that propagates over through the Earth. And this is sort of a solution of a pin on the sphere, just trained for this specific case. And this is like fairly close to like a numerical reference solution. It's a roughly like 5% numerical error compared to standard numerical schemes, which was pretty good. And this is a movement of a Rossby wave. So this is these long range sort of waves that travel around the Earth. So before we had these faster waves, here you see it's much slower waves than before. And also here we get like fairly accurate solutions using pins. So that sort of in a way demonstrated that you could do potentially numerical weather forecasting using physics-informed neural networks. And of course, the downside is here you have to retrain. So the next step for us in this research would be to train an operator network. So if that interests any one of you, that would be a next cool project, training an operator network for the shallow water equations on the sphere. Now let's move on to tsunami modeling. Don't think I have to talk too much about the equations because it's again the shallow water equations, this time formulated in the plane, and this time making sure there is some bottom topography. And the reason why I care about shallow tsunami modeling is because this is really challenging in standard numerical methods. And why is it challenging? Because you have basically a moving boundary problem, right? Like if you have a tsunami, right, you have a coastline, and initially the coastline is dry. And then as a wave or a tsunami wave hits the coastline, in fact, the interface between wet and dry is moving from basically the ocean into the coastline. And in a standard numerical scheme, this is challenging, because like now you have a moving point that you have to track. So how do you do this? If you compute derivatives numerically, if you compute them numerically, then you need a mesh. But then some of the mesh points are at the dry side of the front, some at the wet side of the front, and at the dry side of the front, the shallow water equations don't hold anymore. So people came up with all sorts of ingenious approaches here, but it is a challenging task to solve sort of a moving boundary valley problem. And this, fortunately, is no problem for pins, right? Because there is no moving boundary here, right? Because all we have is collocation points, and I compute, in fact, my derivatives in these collocation points using automatic differentiation. So the wet-dry interface can just freely move, and I don't have to keep track of it. So this was the main motivation why we cared about this. And one classical solution would be, maybe you know about this Kerry Greenspan solution, who actually showed, and this is really cool if you consider the one-dimensional shallow water equations with the linear bottom topography. You can actually linearize the shallow water equations by doing a hodograph transformation. So basically, you just switch the role of the dependent and independent variables. So the independent variables become the dependent variables, and the dependent variables become the independent variables. And if you do this, the shallow water equation is reduced to a linear partial differential equation, which can be solved analytically. And like one particular class of problems that Karen Greenspan looked at is this sort of non-breaking wave hitting a sloping beach. And this is how it looks like. So you would begin basically with like a wave, and this is like a tsunami. You can imagine you have like an incoming wave. The coastline is somewhere here, and as sort of time progresses, you want to keep track of how this wave is moving up and down. And pins, in fact, we are quite accurate in solving this. So it's hard to see it, but there is a dashed line underneath, which is the analytical solution, and the full line is the numerical solution using pins. And this is for two different amplitudes of the wave. So this is the maximum amplitude you can choose in the Kara-Greenspan solution. Beyond this, in fact, the wave would break. So you see it's a quite like strong sort of wave that's coming in, and we quite accurately capture, in fact, how the wave is moving up. In fact, this linear slope. And again, the key point that I want to hammer home here is that we don't need to keep track of this point, which sort of is moving up and down. It's just the nature of pins, right? We have our collocation points throughout our domain in space and time, and just enforcing all of these points the shallow water equation, and then we get the solution that we are getting. And this is for pins. Now we also consider the dam break problem, it's classical problem. So here again, like for pins, as I changed the amplitude, I needed to retrain my pin, right? So this required training and this required training, which obviously is not great for like tsunami research, right? Like in training each of these pins on one GPU took roughly like an hour or so. So it's not great if it takes an hour to compute the solution if you have to give like a warning of a tsunami in a few minutes. So obviously pins wouldn't be suitable for real-time tsunami warning. But what about the deep O-net? Well, in a deep O-net, the idea is you just train on a class of initial value problems that you care about. And so what we cared about is just the standard problem that you have a dam. So basically you have some water, you have a dam in between, you remove the dam, and then the water starts to flow down. And so there is an analytical solution for this benchmark. And what we have done is, well, we simply try to learn the solution operator for the one-dimensional shallow water equations for the class of problems with this analytical solution. So all we did is we sampled at random like 10,000 initial conditions, basically randomly drawing different water heights, like how high is the dam and so on. Where is the location of the dam? Basically randomly just to sample, in fact, our solution space, and then learn the solution operator. And then we train it, in fact, with the goal to find, in fact, the exact solution for one step, for a time step of delta t equals to 1. And then we evaluate this for new and unseen initial conditions. So this is two random samples. The deep O-net has never seen those before. The initial condition, hey, let's start with our initial time at 0.25. Then this is our initial condition, the dots, and the sort of solid line is the deep O-net. And then the solution at sort of 1 time unit later is given by the green line. And same here, just for like a different water height. So there is a different water height here, different water height here. Just that we had seen that we really learned the solution operator. And here, and I think this goes, I want to answer now the question which is in the chat. The one thing which is really good about this, okay, one thing to note, it's really, of course, challenging to capture, in fact, this initial shock, right? So that, yeah, basically this transition region is maybe with further training, this becomes more accurate, right? But there is obviously a numerical error in both of these examples. But the one thing which is really that I want to drive home, right? To get from the blue line to the green line, I just used one step because my deep O-net, which we trained, was trained for basically an interval of delta t equals to 1. That means I plug in my initial condition, and then I get the solution at time step delta t equals to 1. this is just the way I've trained it, right? Obviously, you can train this differently. You could train it like for larger time steps, smaller time steps. But I want to point out there is just a single evaluation of my neural network to get from the solution from blue to green. And this is definitely not feasible in a standard numerical scheme. In a standard numerical scheme, you could not use a time step of delta t equals to 1. It would become unstable and not give you the solution. And this speaks to basically of that this has the potential, of course, to be much faster than a standard numerical scheme, right? Because you can use larger time steps. And this is what I want to now address. This was the question in the chat. Hey, like how much faster can you be? And so we considered again tsunami modeling, right? And so we compare. So this was done with my former PhD student, Rüdiger Brecht. So this was his basically master and PhD work. He developed the standard numerical scheme for the shallow water equation for tsunami modeling using meshless RBF methods. So this is a classical discretization procedure. It's not grid-based, but it requires numerical discretization. And so this was our standard numerical solver against which we compared our new neural network-based solver. So in this method, this finite difference RBF-based method requires generation of derivative matrices. They have to be generated only once and then can be applied. But I just want to point out each time you change the computational mesh, you would have to regenerate these matrices. But yeah, otherwise they can be computed offline. And so this is just to explain this table. So this light gray color is sort of the standard numerical method. So to generate these finite difference operators for this meshless method that we had used like 6 or so years ago takes about 5 seconds. So this is fairly quick. Even if you have to regenerate this, this isn't a whole lot of time. What about the neural network training? So the neural network training for pins and deep O-nets takes like roughly an hour or 3 hours. Deep O-nets take longer to train because learning a solution operator is harder than learning the particular solution. But again, this is an offline cost, right? Like this, you do this once, and once you have it, all you have to do is you evaluate it, right? So once you have trained the neural network, you can just evaluate it everywhere you learn it for. And then sort of for a pin, well, the only thing you can evaluate it for is, well, over the domain over which you train it, right? You just can plug in any, I think this is the one thing maybe that I didn't mention. You train, in fact, the pin for your collocation points, which sample your domain in space and time. But afterwards, once you train your neural network, you can, of course, evaluate your pin everywhere at all points within the space and time domain that you used. This is called the inference step. And this is super quick, of course, right? This takes you just 1 second, right? Just to evaluate the trained neural network at your points takes you 1 second. But still, it's not, and the standard numerical scheme to time step, it took about 25 minutes, right? But so, okay, this is of course already great, right? So like 1 second versus 25 minutes until you realize, well, here, unfortunately, you always have to retrain, right? Like each time you change the initial condition, say you want to predict the next tsunami, well, you have to retrain a network again. So it takes you 1 hour and then you evaluate 1 second. So this is obviously slower than just time stepping with your standard finite difference method. But that's the advantage of the operator approach, right? In the operator approach, you train it, but then once you train it, you can evaluate it for any sort of initial condition. So the evaluation time here is 10 seconds. It takes longer than the pin because it's a more complicated architecture. But this can be done basically offline. So that means if there is a new tsunami warning that you want to issue, you don't have to retrain the network anymore. You just have to evaluate it. And you're vastly, vastly quicker than, right, compared to standard numerical method. And this is why, I mean, obviously it's still ways to go from these very simple benchmarks that I showed you, these benchmarks, to now train this like for a full like complicated coastline. But just to give you an idea, if you can train this, right, you would vastly sort of outperform standard numerical methods in terms of computational time. I think this is also crucial, right, because it's the question which was in the chat as well, right? So this is just the computational time. Of course, this doesn't answer you how accurate it is. And then it turns out, of course, that these standard numerical schemes are typically more accurate than deep ONets, which is why sort of, and I think this brings me to the end of my talk here about like sort of what we talked about and what sort of classes of problems are suitable and what classes of problems are unsuitable for pins. So we talked about most of this already, right? So I think let's start with the last one, right? Like they are vastly less accurate than standard numerical methods. Actually, I can sort of quantify this for you, right? Because I was curious. I solved the linear advection equation, like simplest PDE you can solve with the standard Fourier method and with a pin, and tried to see like how good is my pin. Like I tried to train it as well as I can and then compared it against like using roughly the same sort of number of computational nodes in my finite difference or in my spectral method for the linear advection equation. And the linear advection equation was more accurate, had an error smaller by a factor of 1 million. So the linear sort of linear advection equation to solve with pins just makes no sense at all, right? So standard numerical schemes, at least as of August 2024, are superior in terms of error for almost all problems that you can think of. Obviously, this can change. It's still a very small sort of new field. But so, okay, like this is not great, right? Like if, say, you can solve a problem to arbitrary accuracy or error with standard numerical schemes, you can't do this with pins. You should ask the question, hey, is this really what you should use pins for, right? Maybe, in fact, you should use pins for problems that involve data. And this was one of the questions one of you had, right? So maybe pins are more suitable for solving inverse problems. Somebody gives you some data, and then you want to sort of include this data together with derivative or differential equation information. And then for these types of problems, like standard numerical approaches are really not suitable, because in a standard numerical approach, just can't include very easily additional data beyond sort of your boundary and initial data that's required for the problem to be well posed. So maybe inverse problems is a really good approach for pins. But also, I think coming back to the forward method, there is also problems out there for which you don't require a very accurate solution, right? And this is my motivation for doing this work on tsunami research. Because like ultimately, right, like in the end, you don't care about if you underestimate or overestimate your head of the water by a few centimeters, right? So a few centimeters might equate to like an error, which is, I don't know, 10 to the negative 3, 10 to the negative 2 comparison to standard numerical schemes. But practically speaking, you don't care about this, right? You just want to know, right? Like, does the wave hit like 1 meter? Does the wave hit 2 meters, right? And then if you predict 1.5 meters, but it's really 1.56 meters, it doesn't make a whole lot of difference, right? So I think part of, and again, like people do a lot of research in this field, but my recommendation would be maybe to look into methods, to look into problems for which you don't require a super accurate method. And then some of the advantages of pins, you can easily parallelize training because you can train a neural network in batches. You can use this automatic differentiation. You can do this on very complicated surfaces. Again, for tsunamis, right? You have a complicated coastline. You don't want to use a mesh on a complicated coastline, right? You just have collocation points, right? So I think like for problems like tsunami research, pins are really good. But I'm not sure that like everything that's being done in the literature today is like really meaningful. I have to be honest, because I think people sometimes just do research because yeah, it's a fairly easy to use method. And then once you sort of get the hang of it, yeah, you can solve problems quite quickly and it's still new. So people write lots of paper on this. But my prediction for this field is that eventually sort of some of this research that's being done now might not sort of be done 5 years from now. It's like as everything related to machine learning, right? Like all of this everybody's saying that large language models will replace everything. And I'm not sure 5 years from now if large language models will really have replaced everything, right? And here it's quite similar. So I'm firmly believing that this method is here to stay for the specific classes of problems for which it's superior compared to standard numerical methods, which would be arbitrary surfaces, if you need to parallelize, if you don't need super high accuracy, and if you want to solve inverse problems. And I think if you're interested in this, then I can also sort of point you towards some research, I guess, that I've been doing with like an undergraduate student over the summer. So this is fairly new. We wrote basically, like my undergraduate student wrote like a new library for using physics-informed neural networks, called it PIN-DE. There's some documentation there. So if you want to play around with this, so it's like fairly low coding effort, right? Like how to sort of set up a sort of PIN and solve it. So still lots and lots of functionality that we want to add, and probably lots of bugs in there. But if you just want to toy around and sort of maybe use this like in your own teaching, at least this would be a fairly easy sort of library that you can use. And if you want to use this and feel that there's some features that you think would be useful for your own research and you would like to see in a future version, then please just let us know. It's the short sort of self-advertisement. But yeah, this would be it from my side. And this would be the literature for this field. I think as already indicated, the original source on pins, it's a very readable paper. If you haven't sort of read it or seen it yet, I would start with this paper. It's really well written and includes basically all of the ideas that sort of were then popularized later on for the forward method. And so this is the paper that popularized pins. But they also discussed in the sort of this inverse approach, which I think is really cool. The operator approach would be described in this paper here. And if you want to sort of read more about how this can be done on solving equations in fluid mechanics or on sort of complicated domains like the sphere or for tsunami problems, then these would be our papers. And I think I leave with this, and if you have any questions, please just let me know. Thank you. Thanks for your attention, and thanks for which has been a really long talk. So hope it wasn't too long for you.
Thank you very much, Alex. Very deep and extensive coverage. I like this talk a lot.
Thank you. I appreciate it. Thank you very much.
Yeah, thank you very much for the talk. I wanted to ask actually about whether it's what do you think? It's my impression that it could be useful for solving such kind of many-body problems, like let's say predicting of evolution of orbits in solar system, for example, asteroids or something like this, and that should be more effective. Let's numerical, just ordinary numerical methods.
Yeah. I think that's that's part of where I would like to move my research to, right? So to have like problems where you have data and like where you know the physics as well, right? So yeah, I'd be really excited to try this out. Like your map, in fact, you observe the asteroid, but you also know how it's like how it should be moving. Can you get sort of the trajectories of this? So I think those classes of problems is probably what I would spend my time on, rather than try to solve, say, Burger's equation with pins, right? Like people still spend a lot of time on this forward problem, but yeah, like trying to learn from data. And we've done a little bit of work on this. Like, can you recover conservation laws from data, for example? That I find really exciting, right? So say you have in fact the orbits, right? Like you don't know Kepler's laws. Can you recover this somehow, right? Like conservation of like angular momentum, things like this. And there is like early research that indicates that you can sort of find like conservation laws from data. But the downside is you need a lot of data, right? And then it's the question, is it practical, right? Like if you have to learn sort of Kepler's law by sampling like 100,000 asteroids, right? Is that feasible? And I feel like that's sort of, I think, one of the things, or like one of the selling points typically of physics-informed machine learning is that if you don't have a lot of data, but you know the physics, then you can use the physics, like the differential equations, to fill in fact, for your data, right? So the idea is, yeah, maybe then you don't need so many trajectories anymore, right? Then you just know Kepler's law and just want to do prediction on like one orbit, for example. So I think this will be very exciting, like finding problems where you can solve, yeah, where you have included data and physics together.
I have some questions. You showed where you train operator deep network and you can predict at t like +1 basically.
Yes.
Solution. But does it work only for the like from t0 to t1 or for any?
No, it then works. Yeah, that's a great question that you're asking. So let me share this again quickly. So yes, so the question was, so for this particular problem, I train it from 0 to 1. So I can evaluate then my solution everywhere between 0 and 1. But like, how can I then do time stepping with this? And the answer is because this equation is autonomous, right? Like in this equation, time doesn't factor in explicitly, right? Time arises only as derivative. So for autonomous systems, it doesn't matter, in fact, like once you are at time t equals to 1, you simply said, okay, now my time t equals to 1 is really my time t0, and you continue for another step. So time stepping works for autonomous equations. And most of the equations of, I guess, of like physics and, no, I shouldn't say this, of course, but a lot of equations right out there are autonomous equations, and then time stepping works. For non-autonomous equation would be interesting, in fact, how you would do this, if there is ways how you can try to include sort of the shift in time somewhat in training of the network. But I haven't worked with non-autonomous equations so far.
Mm-hmm.
So
and I also have a question to your experience with selecting collocation points. I wonder if you can comment on having a big set of collocation points, like dense set, and then draw in from this set at each training step. Or you, for example, can randomly select collocation points at every step so that there is no repetition. What is the standard and what works and what? Yeah,
that's a great question. I think it goes back to sort of this loss function, right? So like the one thing that I sort of swept a little bit under the rug is, right, like these are your collocation points, right, for the PDE. And so say you solve like the 3D Navier-Stokes equations, right? So you'd need millions and millions of collocation points for basically any meaningful problem. And then so, okay, what do you do here, right? So then your loss function here would require you to sort of evaluate this at like 1 million points simultaneously, and this is not feasible. So what people do in practice is they use what's called mini batch optimization. So they would sample randomly from your 1 million points. You would sample randomly, say like 1,000 points. You compute the loss and then do one step of your gradient-based optimizer, and then you sample another 1,000 points, another 1,000 points, and so on. So this has shown to work, right? So it takes a little bit longer in terms of, because then like the gradient doesn't point directly to the minimum, of course, it points only roughly in the direction of the minimum. But one thing that has been shown here is, and maybe that goes to your question, that this can be wasteful. Let me try to explain this here. So let's assume, so this is 20 collocation points, and you do mini batch gradient descent, right? So say you compute the loss based on a random sample of 2 points, right? Let's just say 2 points and then another 2 points and so on. And so of course, as you randomly sample, you will always cover all these 20 points. But so initially, right, when you start training your network, there is sort of causality, of course, right? Like for this solution, right, like you need to know that you started here to know that you end up here, right? So when you train a neural network, right, so if you would sample in the beginning of the training these two collocation points, it's not meaningful, of course, on some level, right? Because you need to know what the solution is here first, right? Like it would be way better to first sample these two collocation points, right? And once you sample these two collocation points, maybe these ones, and so on. So there is more advanced ways that how people sample collocation points, like both in space and time, to try to converge to a solution quicker. Like eventually, right, you would also, of course, I mean, here I didn't do this, right? Like here I just sampled randomly and so on, and eventually you recover the solution. But if you are sort of more intelligent, the way you distribute your points and then sample your points in your optimization procedure, the quicker, in fact, ideally your loss function goes to 0.
All right,
And
thank you.
so to add to this, and then of course you could also then check, so say there was a shock somewhere in here, right? Or a jump, maybe somewhere in here, right? And then you realize, hey, maybe you need more points here. So of course it would also be possible to add then further points during training here, right? So it's like this age adaptivity in standard numerical schemes. So people experimented with this as well.
Thank you.
Yeah. Any other questions? If there is no more questions, thank you.
Probably that's. Thank you very much for joining and giving the talk. It was very nice. Hopefully, more in the future.
Yeah, absolutely. I mean, like I said, we're doing research in this field, so do let me know if that interests you, right? If there is any student that are interested in this, reach out. You have my email address now, and obviously I'm happy to answer any questions you may have on this.
Okay, thank you once again.
Have a good day,
Bye-bye.
then, everybody. Take care now. Bye-bye.
Yeah.